So many thanks to the organizers for this opportunity to speak. Um, I'm going to talk about uh, defining Mach's principle, how topology plays in Mach's principle. And here we're defining Mach's principle by saying that local physical laws are determined by the large scale structure of the universe. So the takeaway, what I'd like you to take away from this, if possible, are these points. To calculate with Mach's principle, you need background-free equations of motion. With that, you end up with a model that has no Lagrangian. The solutions of the equations of motion calculate the quantum impedance networks. And this is important because impedance matching governs amplitude and phase of energy flow. This was lost in quantum electrodynamics. So we can impedance match to the Planck length and learn things about the origin of gravitational mass, and impedance match to the universe boundary, and learn about the role of topology in Mach's principle. The model is in flat Minkowski spacetime. Curvatures of general relativity are the phase shifts generated by the quantum impedances. And we'd like to be able to make the jump from the two-body problem to n-body problem in condensed matter. This is not simple, it's a work in progress. So the origin, where things started, was with this paper on the two-body problem and Mach's principle here in 1975. QED, the foundations of QED were set back in the 1950s. And the concept of impedance quantization, of exact quantization, was only introduced to the physics community in 1980 with the discovery of the topological, the scale invariant quantum Hall impedance. So it took another 35, 36 years before this, what we were calculating here was actually understood as the impedance networks of QED. The theoretical minimum of the model, we have three assumptions. The geometry is that of Euclid. We take the vacuum wave function to be the 3D Pauli algebra of space, a scalar, three vectors for the orientational degrees of freedom, three bivector area elements, and a trivector volume element. We get physical manifestation by introducing the coupling constant. So the fundamental constants that define alpha permit us to assign unique flux quanta to each of the 8 wave function components. And then finally, the interactions are modeled by the geometric Clifford product, which is the sum of the wedge product and the dot product. The wedge product increases dimensionality, the dot product decreases dimensionality. So these components have spin, the bivectors spin 1/2 and trivectors spin 1. And when we change dimensionality, then we're changing fermions to bosons and bosons to fermions. So this is a dynamic supersymmetry. The vacuum wave function is the same at all scales. The scale-dependent physics arises from the scale to which flux quanta are confined at the network nodes. And we need a mass gap, a fifth constant here, which is the lightest rest mass charged particle to couple to the photon, and this defines a scale of space. So the quantum impedance networks, again, they were lost in physics. We're interested in basically the geometric and topological impedances. The geometric is near field only, and the topological is both near and far. The one is translation fields, and the other is rotation fields. In the translation fields, the motion is parallel to the applied force, and they can do work. They can be shielded. In the rotation fields, the motion is perpendicular to the force. So you can think of the gyroscope. So they can't do work, they can't be shielded. So the Aharonov-Bohm effect comes to mind here. The one is the channel of local entanglement, and the topological is the channel of both local and non-local entanglement. So it's this non-local entanglement, the role that the topological impedances play as phase shifters and mode couplers that plays into Mach's principle. The photon's unique here because it has both near and far field impedances. So the photon-electron interaction, the Rosetta Stone of QED, this got lost in quantum mechanics. Here, the horizontal axis is the photon energy, So a photon of 0.511 MeV energy is confined to the scale of the Compton wavelength of the electron. At the Rydberg radius, a photon of that wavelength has 13.6 eV. That photon that's coming in here from the right at 377 ohms, the vertical scale here is impedance in ohms, as it sees the electric charge of the hydrogen atom, the electric and magnetic flux quanta that comprise the photon are shifted, the phases are shifted in opposite directions, and Maxwell's equation is broken, that they are decoupled. And the electric flux quantum goes to high impedance here, the quantum Hall impedance, which is also the centrifugal impedance, and that's what permits the ionization of the hydrogen atom. This near field behavior of the photon, you won't find it in the education of the physicist. It got lost in quantum electrodynamics. And similarly, the near field impedances of the electron got lost in QED. So with this, we can establish a correlation between the unstable particle lifetimes and the quantum impedance network nodes. The first thing was to get the electron impedances, which this was done in 2011, and then it was generalized to quantum impedances of the unstable particles. And the two-body problem and Mach's principle was pivotal in this work. So here we see again, we see the impedance network of the electron, the different modes of the electron. Here we have dipole impedances, 3 different dipole impedances. And this is actually the 8-component wave function we're talking about, not just the Dirac equation, 2 components of but rather the full 8 components, extending the Dirac wave function to the full 8 components of the vacuum wave function. So here we have the unstable particle lifetimes multiplied by the speed of light. This is their coherence lengths. It's the boundary of the causal boundary. And you can see the correlation between the unstable particle lifetimes and the nodes of the network. This follows from the fact that impedances must be matched for energy to flow during wave function decoherence. Here we have just a brief image showing the topological inversion of electric and magnetic charge, that the Rydberg is inside the Compton wavelength for magnetic charge, and the Higgs is out here on the outside along. So this plays a major role in particle physics. Impedance matching to the Planck length, well, here we're talking again about this topological duality. The Seeberg-Witten proof of topological duality of electric and magnetic charge. Witten said this was his best work. So what we're looking here was presented to the Rochester conference in 2013. Again, we have the Compton wavelength of the electron with a photon coming in now at a 511 MeV photon. Over here on the left side, we have a primordial photon coming in from the initial singularity of the Big Bang. Here we have the end of inflation at 10 to the minus 32 seconds. This corresponds to what we find in the theories of inflation. And the impedance mismatch from here to here is such that the mismatch is equal to the ratio of the gravitational and electromagnetic forces. So this provides an electromagnetic origin for gravitation. And again, here we see from Planck to Compton, this is a quarter wave resonator. So if we start out at the Planck length with the energy, I actually need to talk about the Hawking photon here. What we're interested in the Hawking graviton is the full 8 component wave function, but here we're just plotting the photon and saying the energy starts at the Planck length in the electric field. By the time it gets out here to the Compton wavelength, it's in the magnetic field, which we know the rest mass of the electron doesn't come from the charge, the electric charge. That is down at the classical radius, not at the Compton wavelength, but rather from the magnetic moment, which is where the energy is by the time we get out here to the Compton wavelength of the graviton that's trying to propagate from the Planck scale. This wave function, it wants to escape. It wants to get away, but all of the energy gets reflected back to the Planck scale, with the exception of the little bit that's necessary to provide gravitational mass to the electron. And similarly, less and less energy is available as you go further and further away from the event horizon at the Planck length. So out here at the boundary of the observable universe, the wavelength is extremely long, and so the phase shifts are very slow, and the graviton at that point is almost topological instead of geometric. And that's what we're interested in, is how that topological effect plays in Mach's principle. We'd like to extend this to condensed matter, and again, that's a difficult problem, that to go from the two-body problem to the n-body problem. So I hope what you got from this, at least a little bit, is that we can calculate, work with a different set of equations, and come up with something that has no Lagrangian, that gives us these quantum impedance networks, which got lost in quantum electronics, quantum electrodynamics. And we can learn things about matching to the Planck length and to the universe boundary both. And finally, we want to work with condensed matter. So many thanks for your time. Many thanks to the organizers for making it possible to give this presentation. And I need to here to end, to stop.